Okay, so what was weird was that I had a rock, it was made up of atoms, and there was energy coming off of it. Okay, for him, he saw it when it exposed X-ray film. Okay, now that's kind of an old example now because nobody ever does film anymore. We all have digital cameras, but for a long time, pictures were taken with film. And so, where's this energy coming from? Because we know that atoms are small, they take up space, but they have no charge. That means they, what we thought, had no energy. Okay. Now, what we found after discovering what was happening, but you see that atom there? What's happening to it? What do you see? It's giving off stuff. Here is the most simple definition of radioactivity. It is an atom falling apart. Okay? The atom is in some way unstable, too big. So it is going to throw away chunks of it and get smaller until it becomes stable. It can actually throw away a chunk, a piece, or alternatively, it can throw out energy. And what Becquerel was seeing was energy, and the energy was in the form of light energy at that moment in time. But the atoms are unstable, and they break apart. That is the most simple definition of radioactivity. And so, if the atom was the smallest piece, it's throwing off little pieces of itself. So that meant that the atoms must have inside of them even smaller things. And so we just kind of said, okay, the atom's the smallest, and now we're finding stuff falling outside the atoms. Okay? What we did discover was several of the particles that were emitted or that fell off were actually charged, meaning that it was either positive or it was negative. Now that really confused us for a while because we knew atoms were neutral, but negative stuff was falling out and positive stuff was falling out. So if we thought about it for a while, we discovered, okay, well, we thought that, all right, the atom must have little things inside of it, some of them positive, some of them negative, but when it's together, it should be all equal, the number of positives and the number of negatives, to create the atom, because the atom by itself is neutral. And so we also discovered through lots of experiments that what was falling off was much smaller than any of the atoms. Okay, so they had charge, and they were smaller. Okay? And so remember, the simplest definition is the atom is falling apart. Now, we don't know where the stuff is coming from. We don't know how the atom is organized. We just know the atom is falling apart. Now, after lots and lots of experiments, we found that there were three main parts of an atom. Some were positive, called protons. Some were negative, called electrons. And some were neutral, called neutrons. Okay? Now, what we did discover about protons, electrons, and neutrons were they themselves couldn't do chemical reactions. Okay? But they came together to create atoms and define how atoms actually do chemistry. So these were the components. At first, we called these particles subatomic particles because you had the atom, and below that, sub was these three particles: protons, electrons, and neutrons. Have you ever heard of those? Okay, and so some people, I'm actually surprised now in elementary school they are teaching students protons, electrons, and neutrons. And can you believe that? I'm like, let's learn our colors, all right? And so, now, all right, we're at theory stage. Scientists love theories. We know small things, positives and negatives, are in there. Okay? And so, this point in time, it was totally up in the air, and there were basically two people that were given credit for coming up with two different ideas about how they were organized. One is J.J. Thomson. I know his name looks like it's spelled wrong, but that's how he spelled it. All right, and he came up with the idea of how it was all put together. He must have been at dinner, and because his theory is called the plum pudding theory. And so I can just see him. Son, the atom is like plum pudding. Okay, so it is a sphere, and what he thought was the sphere is solid, and most of it is positive, and peppered through there like the plum pudding, the little pieces were the negative electrons. So the big amount was the positive stuff, the protons, and the little tiny pieces that were scattered throughout it were the electrons, and there was as much positive as there was negative, and that's how the atom was put together. Now, at theory stage, any scientist can come up with a theory. It's an idea of how things are put together. Now, when scientists come up with a theory, what is the next step? You have to what? You have to test it. Okay? And that's where scientists get excited because they go into the lab. They do an experiment. Okay? And so we design an experiment and we try to test what we think and we produce data and we want to see, does the data match up to what we expect? Sometimes it does, and that's great. But sometimes it doesn't. Okay? And this is where the strength of science comes in, is that at one moment in time, someone may come up with a theory, and then we do experimentation. Does it support or does it refute? If it refutes, then more data is generated that disagrees with our theory, and so we have to come back around, try to fit in what we see, and come up with a new theory. And so science actually changes over time. Now, what we don't see is in college classrooms, in, let's say, a sequence of chemistry majors, general chemistry, what we can teach in 1 year doesn't change. There's research going on, but that's not where we learn it. G-Chem is all the same every time you teach it. And then organic chemistry is the same. But like when we get to biochemistry, how the body works, we're actually doing lots and lots of research. And between one book and the next, the theories actually change. How they explain what's happening actually changes because we know more. And so the further you go in science, the more iffy it becomes, and then you have to interpret what the data is, and things are always changing. And so scientists should be open to taking what comes out, the data that comes out, and incorporating that into new ideas. Now, just like a lot of people, some scientists get pigeonholed in one way to looking at things, and they're not as crazy about seeing new things, but that's what science is built upon. As we get more data, we have to refine what we understand. All right, Rutherford was a contemporary, and he was looking at this theory and thought, okay, let's test this out. If this is true, we're going to try something, okay? And so what he is going to do is use radioactivity, okay? And his radioactivity is going to do this, okay? He's going to take a piece of radioactive rock. Okay, I'm going to draw it right here. So he's going to take a little bit of radioactive rock. And the radioactive rock, remember, is decaying, throwing out pieces. Okay, but the problem is, throws it out in all the directions. Okay, and so he knew it was throwing out in all directions. What he didn't know was it was dangerous. Okay, a lot of the people who worked with radioactivity originally are dead because they worked with radioactivity. They just really didn't realize that it was dangerous. Now, fortunate for him, he wanted to make all the particles coming out in one direction. So what he did was he put it inside a box. Oh, stop it. That is not what I wanted. All right. He put the radioactivity. Will you stop it? Okay. He put that in, and he put it inside a box of lead, which was great. He had no idea, but he protected himself, okay, because the lead absorbed those particles, except for where the little hole was. And his radioactivity came out in a stream. He basically made a radioactive gun, okay? And what he then did was he took something that was very thin, a foil. Now, the foil that you might use and might buy is like aluminum foil, right? Aluminum foil can be really thin, but that was even too thick. And so what he did was he got a metal that would make very, very thin sheets, almost atoms thick, and it's called gold leaf. If you're an artist, you might use gold leaf, and when you buy gold leaf, you can't even touch the gold leaf because it'll break. You actually buy it on a sheet of paper, and then you use the gold leaf because it is so thin, okay? And so what he thought was if he shot those little radioactive material that has lots of speed at this gold foil, then it should hit the gold foil, and it should be like shooting BBs through tissue paper. It should go out the other side, okay, if it's really, really thin, because those BBs should be able to puncture right through those atoms, okay, if the atom was a certain volume and all of the mass, all the weight was distributed evenly. That's what he expected. Okay, and this is called the gold foil experiment. Now, something called an alpha particle will describe what that alpha particle is. For right now, it's a stream of radioactivity. All right, do you see his little box? Here's the gold foil, and then this is a screen. Every time radioactivity hits it, it's going to glow. Okay, so watch. Okay, little pieces. Do you see that it's coming through and it hits the other side? But what else do you see every so often? It's hitting everywhere else. Is it hitting a lot? No, but every so often it deflects. Okay? That was incredible. Because when you look at it, close up, what he thought was the radioactivity should puncture right through, just like a piece of tissue paper. Okay? But what was happening was it hit something so hard and weighed so much that it deflected. Okay? Only a little bit. Most of the time it went right through. Okay? This data did not support Thomson's idea. This data says something's wrong. So Rutherford went back to the drawing boards and started to think about it. He actually won the Nobel Prize for this. And he decided, okay, how in the world could lots of radioactive pieces go through the atoms? Most of them go through and not hit at all. But every so often, they'll hit something and deflect. And so if I look really closely at how Rutherford described it, do you see these spheres? Right here? Here are the atoms. Each one is there. All right? And they take up the same space. But, do you see right in the center? There's a little dot. Okay? This is what he said. The volume of the atom is the same as what Thomson thought. But all of the mass sits in the tiny center, surrounded by a lot of empty space. Now, why do you say a lot of empty space? Because as most of the radioactivity went through, they hit nothing. But every so often, it hit something, and it had to be tiny because there were very rarely that it hit, but it was hard enough to deflect them, either a little bit or even knock them right back at where they came from. Okay? And so he described that center piece that had all of the mass as the nucleus surrounded by a lot of empty space. Okay. Now the animation's there. Here's a picture that's static for you in your notes. He described it in his journal as this. It was quite an incredible event. It was almost as if a gunner were to fire a shell, and in his terminology, fire a cannonball at a piece of tissue paper, and the cannonball bounced right back. And it just flabbergasted him. And that took him on this journey to think about how could you explain what he was seeing. Here is the modern idea of the nucleus and the atom itself, which has stood the test of time. And so in the early 1900s, he came up with this idea, and every experiment from this point on really proves or supports this idea. We have a lot of data now. In the center is the nucleus, and after other experiments, the nucleus has all of the mass. The protons are in the nucleus, the positive ones, and the neutrons are in the nucleus that are neutral. Protons and neutrons weigh about the same thing. That big volume of space that is empty is not really empty. It has the electrons. But the electrons are so small and weigh so little that we don't even, most of the time, don't even count their weight. They're so tiny. It takes like 1,874 electrons to even equal one proton. So in adding and subtracting, they're so small we round them off. Okay? And the nucleus was tiny. Okay? Now, let me give you a representation of how tiny it was. Okay? Anybody been to Neyland Stadium, the football stadium? Okay? Pretty big, right? All right. If you're a student, you don't get good seats. You get nosebleed seats, right? At the edge, at the top end. Okay, think about the edge at the top of Neyland Stadium. Okay? That's the size of the atom. How large would the nucleus be if Neyland Stadium was the atom? Well, it would be a basketball in the center of the field. Okay? Let's talk about, and between them and that little basketball is really nothing, except little tiny fleas roaming around that are negatively charged that are called electrons. And if you did the experiment like Rutherford did, it would be like taking a helicopter above Neyland Stadium and throwing out baseballs over the stadium, and they would fall. How likely would that baseball hit that nucleus, that basketball? Not very often. And that was exactly the experiment that he saw. And that's the kind of ratio that we're talking about. And every atom that we know about is shaped that way. So, the atoms of the chair that you're sitting on are 99.999% empty space. And you're sitting on it. That's interesting. Now, kind of why. We'll talk about that a little bit later. Okay? All right, so 3 things that our atoms are made up of protons, neutrons, and electrons. Okay? And we now know the protons and the neutrons live in the nucleus that make up all of the weight. And then the electrons are floating around in that area. Okay? If you go to chemistry, we take a lot more look at where they are and actually define a whole lot more things. It takes a couple more chapters. Won't go into that much detail. But this is what a teacher would teach at the elementary level. Okay?